All right, so welcome everyone to another session of the String Theory seminars. Today we're very happy to welcome Gerben Venken, who will unfortunately be the only speaker of the day. We had to postpone Daniel Junghans to a later stage, a later date. But in any case, we're very happy to hear today about the large volume scenario and parametric Tadpole constraints. So Gerben, please go ahead.
Okay, yeah, thank you, Pablo. Thank you for inviting me to talk at this very nice seminar series. Yes, so I'd like to talk about what we call the LVS parametric Tadpole constraint. So this is based on work done with Xin Gao, Arthur Heerbecker, and Sim Trier, and this came out a few weeks ago. Good. So this is a seminar series on string phenomenology. So we're trying to make contact between string theory and the world around us, hopefully. And there are some things that we want if we want to make contact in this way. We, the bare minimum things is we want to compactify string theory down to 4 space-time dimensions. We want there to be scaled separation between our external dimensions and the small internal dimensions. We want either a positive cosmological constant that's quite small, or something that at least looks like it on our timescales. And we want, all the moduli that determine the geometry of internal dimensions to be stabilized. And we want to do all of these things in a hopefully controlled regime. So can we do all of these things that we want in string theory? And there's been a lot of discussion about this over many years. And the conclusion at this point seems to be maybe. And well, at the moment, there are, let's say, 2 main proposals to realize 4-dimensional de Sitter vacua in string theory in what's claimed to be a controlled way. These are KKKLD and LVS. And this isn't to say that these are the only proposals, but they're certainly the ones that have received the most attention, and we'll give them some more attention today. So first, to briefly mention KKKLD. So in KKKLD, it's been pointed out by these authors that there exists what they called a singular Bollock problem. And this is a problem where warping becomes deadly for your geometry. So basically, the issue is something like this. You look at your internal geometry, and in string theory, there can locally be regions where the warping of your curvature of spacetime becomes very high. For example, if you're near an O3 plane, this is a point in your geometry where things become singular. And that's fine, because fine, my supergraph description might break down, but I understand how to resolve this in full string theory. But what was pointed out by these authors is that in KKKLD, it's not just small isolated points that become singular, but really, because of the warping, there can be another one part of the volume of Labiao that really becomes singular, so that you are completely out of a controlled regime and you completely lose control. And so this seems quite deadly for KKKLD. Now, I should point out that it has been proposed by these authors that these issues with singularities could potentially be resolved in certain cases, but this comes at the cost of making things very sophisticated, let's say. And then KKKLD is quite far from being the simplest model with Sitter and string theory. Okay, so that's KKKLD. But today I want to talk about LVS mainly. And I want to ask, are there warping corrections to LVS that are similarly deadly as the ones in KKKLD? And I should advertise that Daniel Junghans, who unfortunately isn't speaking today, also in a recent paper discussed corrections to LVS in great detail. Okay, so the person is going to be that to us, we'll see that warping corrections will be very important, but they don't seem deadly yet. And the demand that we avoid these corrections being deadly will lead to what we call the parametric Testable constraint. Okay, so here's the outline for the rest of the talk. First, I'll review some basics of LVS. Then I'll start to explain this warping correction that will lead to a parametric Tadpole constraint. And once we have the constraint, I'll go through some of the implications of V to satisfy it. Okay, so how does LVS work? So we start in type 2B string theory, which we compactify to 4 dimensions on some warped Calabi-Yau. And then for this, we go through a 3-step procedure. First, there's kind of an implicitly assumed 0th step, where we assume that all the complex structure moduli in our Calabi-Yau have been stabilized by flux at some very high mass scale, and that from the 4-dimensional perspective, you can effectively just integrate them out and forget about them. This is something that for the moment, we'll just assume can be done and assume it has been done, and we'll worry about it later. Then the first real step is to stabilize the KL moduli at an ADS minimum, and this ADS minimum will have an exponentially large volume, so that you can get a nice big volume where your supergraphic description is valid. And then the second step is that we will provide some uplift energy. We add some sort of potential energy that raises the minimum of potential from ADS to the sitter. And this will be done using an anti-D3 brain in a warped throat. Okay, so the first step is to get ADS. For this, we consider a Calabi-Yau with 2 Kähler moduli, a big 4-cycle tau big and a small 4-cycle tau small. The volume for Calabi-Yau is then given by this expression. So we have the moduli, and kappa s here is the triple intersection number of the small cycle. So you can work out that for such geometry, the Kähler modulus, the Kähler potential. The Kähler potential, K, is given by this expression, where we have to log off the volume, and then this psi here, where this psi is kind of a topological term. So psi depends on chi, the Euler number of your Calabi-Yau geometry. That's the Kähler potential, and then there's the superpotential. The superpotential consists of a piece W naught, which comes from flux, and then the second non-perturbative term. This non-perturbative term can come, for example, from if you have D7 branes wrapped in the cycle, and there's Gaussian condensation happening on D7 branes, this can contribute a non-perturbative term here. You can then work out what kind of scalar potential you get from this Kähler and superpotential, and they end up giving you a scalar potential with 3 different terms, and you can find the minimum of this potential, and it will be an ADS minimum. So eventually, if you work this out, you get this minimum for your potential. So you see that this minimum becomes deeper the larger W naught is, and it also depends on the volume and so on. And the volume at this minimum is given by this expression. And the important thing here is that this volume is exponential in the size of the small cycle. So the volume is exponentially large, hence the large volume scenario. So if you can make tau s big enough, you can make an exponentially large volume here. Okay. So that's how to get the ADS minimum. And now we want to go from anti the sitter to the sitter by uplifting a potential minimum. So the way to add potential energy is to put in to your geometry an anti-D3 brane. But if you just put in the bare anti-D3 brane, it will add so much potential energy that you don't get the sitter minimum, you just get a pure runaway towards infinite volume without any stable minimum. So what you do is you need a geometry with a warped throat in it. So the idea is that you have, for example, Kelvin-Strasser throat, which has warping, which grows exponentially as you go to the tip of the throat. And because of this warping, the potential that your anti-D3 brane contributes will be exponentially suppressed by your warping A. And in particular, your warped throat will have fluxes on it. So there are 2 cycles here. There are m units of flux on the A cycle, k units on the B cycle, and the total flux in this warped throat n is given by k times m. So there will be a flux n contributed to the D3 tadpole by this warped throat geometry. And how deep this warp throat is set by the fluxes. So the more flux, the deeper the warp throat is, kind of. Okay. So you can regard what the uplift potential you get from your warp throat and you add the trippiness, and it's given by this expression. And I should advertise that the expression here is new in the second version of our paper, which will come out soon. And this is an improved formula for how much the anti-tripping gets warp at the tip. And as far as we know, this is more exact than anything that we know from the literature, in the case without back reaction from the anti-tree brain. But the main, so this is just like a side comment for connoisseurs of warp throats. But the main point here is that your uplift potential has this exponential suppression from the warping, and this exponential suppression is set by the fluxes in the throat. Okay, so we have an ADS vacuum that we start with. We apply it to the sitter, and we want to get the sitter vacuum with small cosmological constant in the end, rather than just getting a runaway. So this means that we want to set our uplift potential to be about the same size as our original ADS potential. Of course, the uplift potential should be a bit bigger, so we get positive one of dark energy, but not too much bigger. And this identification will relate the parameters in the warp throat, which is set the uplift, to the parameters in the bulk labia, which set the ADS potential. And in particular, because you need to match these two exponentials, the small cycle size will be set by the fluxes in the throat, shown here. Okay, so that's how we get LVS and how we get the sitter LVS. But now we want to look at corrections to this story, because you might worry if our original ADS potential has a very shallow minimum, that might be very easy for corrections to the potentials to destroy our minimum. And we will focus here on one particular correction, which we kind of think is the main source of difficulty, and which has a clear interpretation physically and a clear picture of what one should do in order to evade this correction becoming dangerous. Okay, and again, I want to advertise that in Daniel Newman's recent paper, he also studied several other corrections, and that the constraint that we will get in the end is, I think, at least in spirit, equivalent to a combination of different constraints in his paper, even if it's not maybe exactly the same. Okay. So what correction are we looking at? So remember when we constructed our LVS, there was the Kähler potential, which had this volume piece and this topological term from the Euler number. So where does this Euler number term come from a 10-dimensional perspective? Well, in 10D type 2B string theory, there is an R to the 4 term, so Riemann tensor to the 4 term in your type 2B action. And if you compactify to 4D, this term will eventually give this Euler number contribution to your Kähler potential. But this is just a term if you have pure Calabi-Yau. But now if you have a warped geometry and you compactify over warped geometry, then you need to include this warping effect on this term when you compactify. So if you regard what this additional warping does to your term, then you find that it introduces a new piece, this new correction here. And this, if you work things out, will give a new contribution to your scalar potential. So the contribution to the scalar potential that you get in the end is shown here. And now we want to demand that this correction to the scalar potential that we get is significantly smaller in magnitude than our ADS minimum potential, in order that the original ADS minimum that we constructed is still in a well-controlled regime. Okay, so we'll demand this. So we'll demand that the ratio between VADS and correction should be large. So to do this, we introduce this control parameter, C of n. C of n is basically just the ratio between VADS and delta V. And if C of n is 1, then they're just the same size. But we want C of n to be much bigger than 1, so that the correction is small compared to the ADS minimum. Okay, that's one constraint. Another constraint is W naught should be bounded from above, because if W naught becomes too big, then the gravitino mass becomes heavier than the KK scale, and then we don't have a valid four-dimensional supergravity description. That's one way to constrain it. Another way to constrain it, which leads to an even stronger point, is by imposing that certain higher F terms in potential are well controlled, which Daniel helpfully pointed out to us. If you use the stronger constraint, then you again can find a kind of control parameter, C of W naught, which needs to be large in order for these higher F term corrections to be in control. So you get this control parameter C of W naught. Okay, so now kind of putting all of this together and summarizing it again. So we start in LVS with an EDS vacuum, and we want W naught to be quite large so that we get a deep potential minimum initially, but it can't be too large because we still want to be controlled. So C of W naught should be in a controlled regime. Then we uplift to de Sitter with a small cosmological constant by identifying the uplift potential with the EDS minimum. And this identifies the parameters in the throat with parameters at the bulk labia. And now we should demand that our warping corrections are weak enough so that our original minimum is still in control. So we demand that the C of n should be significantly bigger than 1 to be in control. Okay, so if we put all of these constraints together, then one can obtain a constraint on the flux n in the warp throat that is required to be in a controlled regime. Okay, so you can give an analytic expression for the constraint on n in terms of Lombard W functions, but leading behavior is shown below. Basically, you find that n should be equal to this n star, which is set by Gs and m squared, times these very slow rhythmic terms. So there are some logarithmic terms depending on the topology of your Calabi-Yau. That's one depending on the non-perturbative effects from the gene condensation. But most importantly, there are these two logarithmic terms coming from the amount of control you want to have. And you see that the more control you want to have, the larger n needs to be in the warp throat. So the more flux you need in your warp throat. But it's important that this flux n is giving a positive contribution to your D3 tadpole in your geometry. And the total amount of D3 tadpole in your geometry should be 0. That's just Gauss's law. So you need a source of negative tadpole in your geometry that's large enough to compensate for this positive contribution coming from n. So the total amount of negative contribution to your D3 tadpole coming, for example, from O3 planes or 7 planes should be at least as big as n. So that's our LVS parametric tadpole constraint. That's the main result. And well, let's go see what the actual numbers are that we get for this. So firstly, GSM squared should be set to around 46 in order for the warp throat. Well, it should be at least 46 in order for the warp throats to be stable. It can be more, but let's just set it to this value. The topological parameters K and Xi in the Calabi-Yau threefolds are order 1, so we'll just set it to 1. This number A of S from gene condensation is pi divided by 3 for just the stack of D7s locally canceling out 7 planes, so we'll set it to that. And then with these numbers all set, all that's left is choosing how much control you want. So let's say you set both control parameters to about 5, which is really about the least amount of control that you can reasonably ask for. Then you see that the amount of flux n in your warp throats needs to be 92. And if you want to have, a more serious hierarchical amount of control, then these two control parameters, let's say you set it to order 100, then the flux n in the throat needs to be around 140. Okay, so we need negative tadpole to cancel out the tadpole coming from the flux in the warp throat. And if you have 2 scalar moduli, like you need an LVS, then the largest amount of negative tadpole that's known is 149. So it's 149, which is more than 140. So that's good. But you need this negative tadpole for more than just the flux in the warp throat. So, okay. So remember when I was telling you about how to construct LVS earlier, I said there was this implicit zeroth step where we assume that all the complex structure moduli have been stabilized by flux at some very high mass scale. I just assumed that this could be done, but it's not pretty clear that this can be done. So, for example, in this cranial manifold, the one mentioned here, just 149 units of negative tadpole. For this one, you have hundreds of complex structure moduli. And if I'm using 140 of my negative tadpole to cancel out the flux in the throat, then I'm only able to turn on 9 fluxes to stabilize hundreds of complex structure moduli in my labia, which is maybe not ideal. Okay, so so Chris already said this, but then things might even get even worse, because in addition to our parametric tadpole constraint, there has been proposed this Testable Conjecture by these people, which basically says that if you have a smooth calabi-yau, and your smooth calabi-yau has a large number of complex structure moduli, then often the number of, or well, they say in general, the number of complex structure moduli will grow more rapidly than the negative tadpole grows as required to stabilize the complex structure moduli, such that you cannot stabilize manifolds with a large number of complex structure moduli parametrically. Now you might say, well, fine, just look for manifolds with a small number of complex structure moduli, but with a high negative tadpole. But that's, I mean, that's not really possible. Usually, if you want to have a high negative tadpole, you also expect that there will be many complex structure moduli present. So this might lead you to an issue like this, where this is the amount of negative tadpole in your manifold, and you want it to be at least a certain amount to satisfy your parametric tadpole constraint and be able to have sufficient flux and inner throat. But on the other hand, the negative tadpole also cannot be too much, because then you won't be able to stabilize all the complex structure moduli. And the situation might be like this picture above, where there's this intermediate regime where everything is nice and you can have LVS nicely, but it might also be like this bottom picture where these two intervals overlap and there's just nowhere that you can actually have a nice LVS controlled setup. But I should mention, firstly, the Testable Conjecture is, of course, conjecture and not something that's proven, but also that the conjecture only applies to smooth geometries. And in fact, it was shown that it's possible to stabilize all the complex structure moduli if you allow for singular geometries. So maybe we should embrace geometries with local singularities and then use non-abelian gauge geometries on those local singularities for Fino reasons. Maybe that's not too horrible. Okay. So there's some more comments on how to satisfy this parametric tadpole constraint that we found. Firstly, it's important that our constraint comes from having the warped throat and using that for the uplifts. But there have been alternatives proposed for uplifting from ADS to de Sitter, for example, winding uplifts, T-brains, a T-term uplift, and none of these use a warped throat, so our analysis doesn't apply to any of these. So maybe it's worth investigating these further, seeing if these can be done in the controlled range string theory and so on. But if you want to uplift with entity-free brains, then you need a suitable geometry to satisfy our constraints. So you need to find models with a large enough negative tadpole. So, okay, so then you need to find right calabi-yaus to have a large enough negative tadpole. And, well, what do you need for negative tadpole? Well, you need more O3 planes. You need D7 brains wrapping a device with a large order number that will give you a large negative tadpole. But it's, of course, easy for me to say, well, just go and find me a better calabi-yau, just find me one. With more tadpole, it's easy to say that, but it's not easy to actually do, of course. Good. Okay, then another thing is LVS uses 2 Galen moduli, but maybe we should consider calabi-yaus with more than 2 Galen moduli. If you allow for more than 2 Galen moduli, the other parameters can also get larger, you would expect. And in fact, you know that if you allow for more than 2 Galen moduli, you can get a larger negative tadpole. But the issue now is that you need to be able to stabilize more than 2 kilomoduli if you allow for this, which is also not obvious how to do this in a controlled way in LVS. So in general, we expect there to be a kind of trade-off between more complicated geometries, on the one hand, providing a larger tadpole, but on the other hand, allow introducing new difficulties of their own. Okay. So maybe the most extreme version of this is to go from type 2B to F theory. So in F theory, if you look at fourfolds in F theory, you can realize very large ordinal numbers, and you can realize a very large negative tadpole. So for example, negative tadpole of around 70,000 was realized, which is much more than we need for our constraints. But well, then you also need to deal with all of F theory. You need to deal with modularized superposition F theory. You need to ensure that you're in a controlled regime where LVS works in F theory. So there is on average a small G string. But maybe it's interesting to add LVS in an F theory setup. For example, in F theory, you'd expect these topological parameters. For example, this parameter xi, which is typically order 1 and type 2B, maybe you can make it parametrically large in F theory, and then you can use this to get a large volume in LVS, because the volume in LVS depended exponentially on tau s. And normally you can get tau s quite large by making G string very small, but you can also do it by making psi large if that's possible. Okay, so with all of that, what's the way forward according to us? Well, it may be difficult to realize a large tadpole, but the situation in LVS, it seems to us, is very different from the current situation for KKKLD. In KKKLD, you have the singular problem, and it seems dangerous, independent of the concrete topology of your Calabi-Yau. But in LVS, there's a complete road towards parametric control, but we need to figure out if geometries with the right tadpole and the right topology exists. The roads that you need to go is clear. Okay, so in conclusion, in LVS, it seems to us that the main challenge right now is being able to realize a large enough negative tadpole such that the flux and in your throats can be sent to a regime where you have sufficient control over warping directions. And it really seems to be the main thing, ask whether this is possible. Okay, thank you. That's it.
Thank you very much. We have some time for questions. If anybody has a question, please raise your hand or simply unmute yourself and shoot. If not, maybe I can start with a question. Is that basically this constraint comes from demanding that you can neglect this extra correction that you estimate. Can you show that actually that correction destabilizes the vacuum, or if you could take it into account and compute how it affects the minimum?
I don't think it's obvious whether, for example, you need to worry about what the sign of this correction is to see whether it's, creates a runaway or doesn't. And I don't think it's obvious what the sign is in general.
Right. So you cannot compute it explicitly in full detail, but do you know, like, for example, if one sign would destabilize and another one would?
You know that for one choice of sign, there is for sure a destabilization, I think, towards 0 problem, if I remember correctly. You know for sure that for one choice of sign, this happens. I don't remember if it's a plus or minus sign off the top of my head, but you know for sure that for one choice of sign, it happens.
And the other sign is good, I think. The other sign makes it more, does not destroy it.
Yes, exactly.
Is there a way to compute them, or? Is it too far-fetched?
Gerben, can you show the integral?
Yes. So I mean, wait. Yes, this is. Yeah. So it's basically this it's a new term in the attendee perspective, right?
But it's not.
But this happens kind of from integrating over the warping in your entire Glabio. But then it depends on the overall sign if you integrate overall the warping, let's say. But it's not obvious, I think, what the sign is. I'm not sure if it's how viable it is to actually estimate the signs.
Okay, thank you. Thomas has another question.
Yeah, thanks, Gerben. I was wondering, I never really followed the topic too closely, but I remember there were papers in the past claiming that alpha prime took corrections to LVS sort of correct killer potential similar to warping corrections. And I thought there was a debate that it was difficult to understand which one is the leading effect. Is that correct? And would it not play a role here?
I'm not sure. I mean, these up to the fourth term, this is also, I mean, after the fourth term,
yeah, it is an alpha prime correction.
It's also an alpha prime correction, right?
Yeah, but there are corrections from higher orders in alpha prime. Yes. And I thought there was a discussion that if you had warping corrections to LVS, they sort of are similar to the higher order alpha prime corrections, or is that wrong, what I'm saying?
Well, I mean, this term, for example, is coming both from, warping and alpha prime, let's say, but we also use alpha prime corrections. So, for example, when we constrain W naught here, this bound W naught that comes from higher F terms, this comes from alpha prime corrections.
Okay.
And they have to be also. Yeah.
So you think that you have the leading correction to the standard picture? That's what you're saying?
I mean, I think we think that these are the leading terms. So there are, for example, also proposals for certain logarithmic terms, logarithmic corrections to LVS, which I think if they are there, they are more leading than what we have. But I never fully understood whether these corrections actually exist or don't. For example, by Antoniades and by Ken? No. This is from the other paper, I'm not sure.
Wasn't it Joe Conlon who emphasized?
Conlon, sorry, yes, Conlon, yes,
yeah.
Conlon. Yeah.
Okay, I understand. The point is that this is specific to the sitter uplifts, right? I mean, that is crucial.
Yes.
Okay, thank you. Yeah.
Well, it's not the sitter uplifts, even it's specifically KKLT like throat uplifts. I mean, the one way out is to have other uplifts, of course.
Right, sorry, that's what I meant, yeah.
Yeah, so and that's very interesting. I think it's maybe also a promising way to go rather than looking for large tadpole to look for other uplifts.
Mm-hmm.
I mean, there are other uplifts. I don't know. So actually, I did not study well enough what the feeling is. How if you go into all the details of say T-brain sputum uplift, how confident you will feel after studying this in all detail.
Okay, thank you very much. I see no more questions. So then we can just thank Gerben again and wrap up for today.
Yes, there's one more question, I think. Isn't there Vincent?
Oh, Vincent.
Sorry, no. Sorry.
He was clapping.
I was clapping.
the wrong
Anyway.